6. I got 6. Maybe we can start some discussion. This is about where we will have a test, the first test. We've covered the stress calculation in multiple layers. We've covered the failure theory, how to assess whether a ply is going to fail or not. That is sufficient to actually do some designs. And then we're going to cover today last topic in that series, which is the stiffness requirements for a laminate. Now, we are ready with these to have a test so that I can test your knowledge in each of those. But it will not be in the spirit of design exercise, the test, because I don't, I can only ask you how many layers I may need so that it won't fail. So it's kind of a design, but it's not really a detailed design exercise. Or I can ask how many layers of certain orientation angle to make sure that certain stiffness property requirement is met. So those are the kind of questions that I'll be able to ask. I was thinking about this yesterday, and instead of giving you a test, we can turn this into a little project that I can give you some requirements, a little bit more complicated than the one that you will have in the test question, because then I'll be able to make it sound more like an integrated design problem where you have, for the same laminate, stiffness requirements and strength requirements to be met. And this project will become your first test, and you will have maybe a week or two to complete this. I have the majority joined us already, 7 individuals. So any thoughts about this? The 8th attendee is just joining us. Matthew just joined us. Alex says he likes the project idea. Can we turn this thing into a little vote? 2. So the idea is turning the first test into a mini project that you will be designing a laminate to meet some strength and some stiffness requirements. This is a little bit different than a test. If I were to make a test, I wouldn't be asking something more integrated, like design a laminate that will have both stiffness and strength requirements. I'll have to chop it off to small pieces, and for the test, I'll perhaps say, okay, this laminate has this many layers, and you're able to change the number of layers of this orientation and that orientation. Find a laminate that meets this, the number of layers of certain angle that means stiffness requirement. Or I will ask a question about strength requirement separately. Or I will ask whether certain laminate will fail under given laws or not. So instead of making a test like these little questions chopped into pieces, we turn this into more of a project sounding thing that you design one laminate with multiple requirements, and it's a little bit more general. It's more open-ended. There's no one answer. We'll be able to compare different answers and that people will be getting. And there's no optimization. We haven't studied optimization yet. We're going to do that as well. We're going to do actually optimal design projects out of this. But it will be a more integrated question, and you'll have 1 week or maybe more, a little bit more, to complete this project. And that will be your first test. All right, so that's 1, 2, 3, 4, 5, 6. Yeah, absolutely. Actually, you can spend the office hour periods with more participation, with multiple questions, and we'll be able to actually try to form a general way to not everything, to solve everything and solve the entire project, but I will give hints to solve the pieces of it. All right, so Matthew, do you have an answer to the question test versus project? I've got project. All right. I think majority now says project. Let me make, just in case, a count with my so that let's see. Q says P. Okay, that's a P. Alex P. All right. Paul starts with P. And that is correct so far. The answers that I don't have is from Samuel and Mohan, Hare Krishna, and that's it. All right. So, okay. How do I do this? Do I want to also give a test, separate test for those who prefer a test? I can do that. I can do that as well. So we're going to do a project, but if there's somebody who really wants to make a test, send me an email and we'll make a test for them. Okay? You don't have to answer it right now. You can do it via email to me, but we'll be able to do that. All right, so let's go back to Oh, yeah, let's put some time around this. Course documents. I'm in the wrong course. This is fall 2020, 2000s. Composites is over here. Spring course documents. 2/11, today's date. All right, today is here. Project assignment. I will and we'll put a date. You'll have the wellness holiday weekend there. So this is lecture 16, Tuesday, Thursday. There's weekend, Thursday. This is, oh, so this is yeah. Okay, so 302. That's the due date for the project. And I'll start putting the project description right after this class on a piece of paper, and hopefully the first version will be available by tomorrow, sometime tomorrow, hopefully. So let's make this to be red text. Red text. All right, and the material that we will cover today is possibly part of that equation as well. So we're going to do laminate in place stiffness sort of quote-unquote design. All right. Any questions? So let me go to my lectures and do the lecture very quickly so that I can actually show you the proper design. All right, I may need I may need full screen writing slideshow so that I can make blue pen. All right. So we're gonna actually have looked at entire laminate, and we now know how to how the different ply orientations influence the stress state within the laminate, and from the stress state you can go and compute whether the laminate fails or not. And so we're ready to implement this as a design idea. The second aspect of the composites is sometimes you have buckling and vibration constraints from structural analysis. Those are stiffness-driven quantities. So you actually need constraints on some of the stiffness properties. So as a simplification to this overall stiffness design, just like I did in the strength, I'm going to limit myself to only in plane. So there's no bending, no curvatures, nothing else. So through the thickness, strains are same everywhere. And then there's A matrix, no B matrix, no D matrix, no bending. And we're going to look at the stiffness properties. Now, along the way, we'll also introduce at the end of this something called lamination parameters. These are extremely useful idea that is very, very useful for design purposes. But the first project is not going to involve lamination parameter design. So I'm going to actually probably cut short of this lecture when we come to the Mickey's diagram and lamination parameters. So we're going to mostly concentrate on the effective stiffness properties today. And then I'm going to do the tutorial on this so that we'll understand the influence of different fly orientation angles on stiffness properties so that we can design with them. So what do we mean by effective in-plane stiffness properties? Because we only have now, we know fiber modules E1, we know E2, G12, mu12 for one layer, but we stacked 30, 40, 50, 100 layers, and we formed a laminate. And this laminate has some overall stiffness properties. Where are they? They're all built into this A matrix that we talk about, which is the relationship between the laminate midplane strains and stress resultants. Okay? And these stress resultants, ends, come from this, which are the through the thickness integral of individual stress components from minus h/2 at the top surface to h/2 at the bottom surface of sigma x dz. And the sigma x's for each layer as the z coordinate changes come from here. That the sigma x at the given z location, which defines as certain ply, kth ply, it's related to q bars of that particular ply times the strains, which based on the fact that there are no curvatures, these are also epsilon 0, epsilon y 0, gamma xy 0. Strains through the thickness are same everywhere. Okay? Now, at this point, we take this relationship between stress resultants and strains and turn it into a relationship for the entire laminate between stresses and strains. How do we do that? Since this was through the thickness integral, this was the stress resultant. If we divide that the nx, ny, nxy, this should have been y, nx, ny, nxy by total laminate thickness, you get the average stress in the laminate. So I have a laminate, I'm able to apply strains, and it generates some internal stresses. Integral of those internal stresses at any point give me nx, ny, nxy. But if I divide that quantity by the laminate thickness at that point, I get some sort of an average stress at that point in the x, y, and tau xy direction. And what I do is I use this relation now as stress-strain relation, and I call this matrix not A matrix, but A star matrix, which is divided by H. A divided by H. I call it A star. And then I compare that relationship to in-plane stiffness properties of a layer, orthotropic layer, which has some EX, EY, EXY, and if I take the Q for it and divide it, that will be, I assume that to be H, I can actually make the comparison between these two, and I can solve these for EX, EY, and GXY in terms of the A's. So my overall effective stiffness, EX, is now written in terms of this A matrix. 1 over H, A11, A22 minus A12 squared divided by A22. This is sort of a modulus for the entire laminate in the X direction. So given the A matrix of a laminate, which could be 100 layers, 200 layers, as long as I can compute the A matrix for it, divided by the total laminate thickness, I get a modulus for the entire laminate in the X direction. And then similarly, there is a relationship between EY And that, the only difference is now this divides it by A22, this divides it by A11. And EY, modulus of that entire laminate in the Y direction, is from the A matrix computed this way. The shear modulus is simply taking the A66 divided by H, and the Poisson's ratio is the ratio between A12 and A22. Okay? These are now my effective properties of my laminate. This is what we're going to be using in our design study. And I'm going to show you an interesting way of looking this EX, EY, GXY, new XY by creating some polar plots. Now, we're going to continue a little bit more with this lecture, but I'm not going to complete the definition of what I call Mickey's lamination parameters. But let's continue a little bit more. This is what's going to be useful for our design study. These laminate stiffnesses not only can be written in terms of the A matrix, but it turns out that they can be written in terms of material invariance, the U's. That's capital U1, capital U2, capital U5, along with fiber orientation angles. How? We know that these sigma x, sigma y, tau x, y are written in Q in terms of Q's. The Q's are numbers for a given orientation layer, but there's also an equation for it, that Q11 bar is actually equal to material invariant U1 plus U2 times cosine 2 theta, that angle orientation of that particular layer, K layer, and then plus U3 cosine 4 theta. So instead of putting these Q's in there and making comparisons, we actually do the integration with these quantities, with these expressions. Now, when I do that integration, I define a bunch of new quantities based on these. I define something called V0. I define something called V1, something called V2, V3, and V4. Okay? And V1 is defined V0 is defined once for A matrix. By the way, this is not only valid for A matrix, but also bending properties and coupling properties as well. So V sub-0 super A, V sub-0 super B for B matrix, and V sub-0 super D for D matrix. V0 is simply H. For B matrix, it's 0. And for D matrix, it's H cubed over 12. V1 for A matrix is integral from minus H over 2 H over 2 cosine 2 theta times 1 dz. Why? Just this jumps all by itself. I don't understand. While I'm talking, it just suddenly jumps all by itself. V1b is integral cosine 2 theta z dz. V1d equals h over to h cosine 2 theta z squared dz. For us right now, for only A matrix, only this and this and this and these are going to be useful. We're not going to worry about B and D matrix. So B1 will be h over 2 to h over 2 cosine integral of cosine theta dz. Cosine theta actually is not continuous. I jumped again. Cosine theta is not a continuous function, but it's actually a piecewise function. So we made plots of theta as a function of z. This was z, and we said, okay, at this angle theta. So the z variation was maybe 45 degrees, then minus 45 degrees, then 30 degrees, then minus 30 degrees, then 0 degrees, then maybe again some other angle. So this is a piecewise variation, but we're writing as continuous. So that means these can be turned into summation as well. But as definition, V1 is integral of cosine 2 theta dz. If we do that, we get matrix form of V0A, and A11 will be U1 times V0A plus U2 times V1 of A, and no V2, and U3 times V3, and no V4. If you look at A26, so to read this table, what you need to basically say, let's take, you're not going to be doing the D matrix, but if I was looking for D11, that would have been equal to V0 super D times U1 plus U2 times V1D, that's this term, no V2 term, 0, V2 term, V3 term comes with U3 plus U3 times V3D. Okay, that would have been D11, where those things are actually integral of those quantities. So for a symmetric laminate in-plane stiffness matrix, the A star is A over 2, some constant U's, plus another constant matrix times V1 star. I jumped again. Another constant matrix times V3 star, where these V1 stars and V3 stars are through the thickness integration of the ply orientation angles. That V1 star, V1 was integral, V1 star 1 over H minus H over 2 to H over 2 cosine 2 theta. Jumped again. What is going on? Something is touching somewhere, I don't know what. And then V3 star is cosine integral of cosine 4 thetas. You see, we again split the designed quantity A into some material property constant times nothing, plus another material quantity times integral of the orientation angles, integral to V3. So, in fact, for this problem, A star matrix is defined completely by two quantities, V1 star and V3 star, which is integral of these. After this, we are going to start calling them as lamination parameters. And instead of the integral, we're going to replace the integrals with summations. And we're going to come up with these new definitions. But that, I will do it in the next lecture. We're not going to do it. And then we're going to be able to generate very nice plots called Mickey's diagram that you'll be able to actually design. Regardless of the number of plies, it doesn't matter how many plies you have, you will see that each point in this diagram will be some stacking sequence that will meet all of our requirements, stiffness requirements. Okay, but we're gonna start doing that next lecture. So going back, now we're gonna concentrate on what we call these effective intrinsic stiffness properties for the laminate, EX, EY, GXY, and UXY. Any questions so far? Questions? It's 7-1. Mohan also wanted a project, so let me mark that as well. And are we still missing? So the lamination parameters are a function of what ply angles you are using. That's absolutely correct. So everything about orientation stacking sequence design is lumped into an integral of all of those 5 orientation angles. Even if you have 100 layers, you integrate them, and you'll be able to write the A matrix for that laminate. So here, so the A matrix here is all of the high orientation angle information is in these V1 star and V3 star. So regardless of the number of layers, the A matrix, if I assume them to be unknowns, V1 and V3 star, if I have a stiffness requirements on A11, that A11 has to be certain number, I don't have to know the orientation angles. I can actually find as a continuous value what this V1 star is and V3 star is. I can actually be able to analytically solve it. And then any laminate that has integral of the orientation angles that meets this will be acceptable laminate. And there will be hundreds of different laminates that I can use that will meet the same design requirement in terms of stiffnesses. This is the crux of the matter. So it's really very nice thing, but we're gonna learn how to do that in the next lecture. Okay. Any other questions? So, by the way, the reason I said this is if you're not reading your messages, Alex was asking if the lamination parameters are only functions of the ply angles. Yes, the answer was yes, and integral of those through thickness and regardless of the number of layers that you have. And you will see that actually these V1 stars and V3 stars are normalized quantities, and they only vary between -1 and 1. Because cosine to the integral of cosine theta divided by the thickness. All right. Any other questions? Let me get some tea. And let's go and do our tutorial that you will, I think, find interesting because we see these equations all the time, and sometimes imagination about this particular thing. Whether I should have recorded this lecture because Samuel is not there. Samuel is not there. I didn't record, but I can start recording now. All right, so I'm going to go now to the tutorial. Let me minimize this. And by the way, this lecture and tutorial are on Blackboard. Okay. And this is the tutorial. All right, this is 200. I guess that's enough. don't know if I asked this. 200 versus 300. Do you have is this readable enough for you guys? Or do you want to increase it to 300? Do you have anybody who is older than 45 in this group? No, I guess looking at the photographs, you're all younger than 45. So I can reduce it to 100 actually. You don't even need 200. You should be able to read it even with 100. No, I'll keep it. All right, so let me load my composites module. Open recently 2021 module for FAM language and run all the code. And now question mark composites should respond. Yes, it does. And what we're going to spend time today will be something called polar plot moduli and effective laminate moduli. So we need ABD matrices as well, but we have the in-plane effective properties defined as 1 over H times these A's. Okay, and I'm going to demonstrate the influence of different orientation angles for 3 different laminates here. I chose 3 different laminates for a reason, but 1 layer laminate is like an orthotropic layer. Okay, then we're going to do 2 layer laminate, and then we're going to do 3 layer laminate. So laminate 1 is theta 1, laminate 2 theta 2. Theta 1, theta 1, theta 2, theta 3. I do not know what those are right now. I'm going to leave them as symbols. But I'm going to do this for a specific material property called glass epoxy, and I'm going to use layer thickness of 0.01. And first module that I want to look at is called effective laminate moduli. What would this do? If I give a list of stacking sequence, and if I provide the invariant material property U, and if I have the thickness, it will compute EX effective, EY effective, GXY effective, and UXY effective, and give it to me, give them back to me. This is just like calling A matrix. Okay, we were calling the A matrix with the same quantities as well. This time, instead of giving me the A matrix, from the A matrix properties, it's going to compute the effective moduli. All right, so effective laminate moduli, laminate 1, and I know what the U vector was. I defined layer T. They are here defined, up there, right here, and right here. So laminate 1 is single layer, theta. And if I use theta equals 9 degrees, or theta equals 9 star degrees, you can see that this is some quirky thing that I needed to demonstrate. That since the effective moduli works with angle input, that is symbolically. So if I put a symbol theta 1 and then in the call, if I make it theta 1 and then assign a value, it turns out that this is not the way to do it. You have to say degree to it. That actually, if I type putting any degrees in there, this is what I get. And laminate 1 was theta 1, so there is no degree sign in here. if I put 45 in here, I have to convert it to a number. So this is already computed as effective moduli by calling this. So I computed it symbolically, okay? But if I want the laminate one, first assign the data as 90, which means basically sending in into effective moduli this thing. Then I don't have to say afterwards anything with degree. I can basically use this construction. So this is going to do the same thing. And for 90 degrees, this will be the effective EX, this will be the effective EY, GXY, and new XY. So these are the effective properties. And if I take the laminate one and do this, for a 30 degrees, it also puts a message in there that says the material has coupling behavior. So the key assumption in getting the effective moduli, there is no A16 and A26. Did you see any A16 and A26 in the equations? No. So even if you have E16 and E26 in the laminate, you can do this, and you get the effective modules in the X direction. By the way, to do the X direction, I need to do one here, which is the modules in the X direction for 30 degrees. But it warns you that actually these are not zero, A16 and A26. So the quantity that you observe as EX is prone to being not accurate, okay? Because you actually have coupling in the length. So for any orientation other than 0 and 90, an orthotropic layer will have coupling. If it's 0, it's clean EX effective. If it's 90, you have a clean EX 8.27. 10 to the 9. So you can see this is 3.8, 10 to the 10. EX is much larger than EY. All right. Now, what use does this EX has for us if we are dealing with stiffness requirements of a laminate? Well, directionality has everything to do with this. Laminates, whether we like it or not, individual layers have directions, and you can make a composite laminate that will still have directional property. It's not isotropic. It behaves differently in different directions, okay? And I'm not just gonna be interested in a laminate, its stiffness property only in one direction. I'd like to know its stiffness properties in possibly every given direction. So I create what I will call a polar diagram of the effective stiffness. What does this mean? I'm going to take a point in the laminate and not only look at effective stiffness in the X direction, but I'm going to look at the effective stiffness in the 5 direction or 10 direction or 30 degree direction or 40 degree direction. In every possible polar orientation around that point, I want to know the stiffness values of this laminate. To do that, I'm going to put another angle phi, which will be the direction that I'm going to be looking at this point. So if I have a laminate 1, and if I'm looking at it from a direction phi, it's going to be as if I write my laminate in laminate 1 minus phi direction. Okay. The new laminate as I change my feed direction. My new laminate is my old laminate minus feed. Even if I have more than one layer, it'll do for more than one layer. This is a list. This is a scalar quantity. If this is a list, it takes. So I can show you actually. I could have done this for the laminate 2 as well, which I will do later on. But in that case, it's going to generate minus phi plus theta 1 and minus phi plus theta 2. So laminate 2 was theta 1 comma theta 2. Now the new laminate will be like this. And then I'm going to be looking at its effective stiffness in that direction by, say, for the 30 degree, theta 1 equals 30 degrees. And this is the effective stiffness of that layer in that 30 degree direction. And out of this, phi I can be changing. I can be making phi to be slash dot there's phi. Also 30. Suddenly it became a constant. I can be looking at 180. Oh, it's different value. So I make a function out of this. I think I should have called this not theta, but E. But it's in the definition. And effective. The function, I'm going to call it E sub phi. As an argument, it will take an angle. This poor choice of angle there, theta. It has nothing to do with this angle theta. And I'm going to compute the effective laminar modulus of this laminate with the theta 1 going to theta degrees. That's this one replaced by this theta. And this will be my function E sub phi. For the 30 degrees, it's going to be, oh, this is the theta, yes. So I'm not doing the theta here, but I'm doing the theta here, but I'm doing theta here. So theta is a good choice. Then I'm going to make a polar plot by changing phi from 0 to 2 pi. So this will be the effective moduli of a 30 degree layer, looking at from every direction between 0 and 2 pi. And sure enough, this is a polar plot. The highest stiffness is in the 30 degree direction. This is a layer which is oriented 30 degrees. And the lowest stiffness is 30 plus 90 degrees, 120. And that's the weakest stiffness direction. And in any other direction, if I am looking from the x direction, this is the value of the modulus, effective modulus. So you can clearly see how biased this stiffness property is with respect to this 30 degree orientation angle. And I can put a little bit more meat around this, make the polar plot of this with some more labels. And this is for, where is the 0 degree to 360 degree of a 0 degree ply. Okay. If you want to see the polar plot for the effective stiffness for a 9-degree ply, so the stiffest direction is this, but in the X direction, it has a lousy stiffness. A 45-degree ply will have the largest stiffness in the 45 direction, lousy stiffness in that direction. And so is minus 45. It will be this way. So largest stiffness in this direction, lousy stiffness in the 45-degree direction. And if I want to normalize this, I will normalize this with respect to E1. So I take the ply materials. This will give me E1, E2, G1 to mu1, 2 for this thing. And take here the E1. So normalize, I'll go use normalized E1 value of 3.86 by dividing this E sub phi by norm E. So my plot now is with respect to 1, where 1 is the modulus of it, so 45 degrees. This contour is equal to 1. Okay, you'll see the use of this later on as I do go to 2 layers and 3 layers. So 25.75 layer. This is the largest stiffness, which is normalized 1. In any other direction, in the perpendicular direction, this is only 20% of the longitudinal modulus. So if you're here, this is, I think, 50% of the, each slice is 20%. So this is 20%, 40%, 60%, 80%, 100% of the overall stiffness. Then I can actually use manipulate for this function and put here theta and change theta from minus 90 to 90. So for 0 degree, that's what I have. For any other orientation, I can see how the stiffness properties are viewed from different directions. So for 9-degree ply, this is the strongest direction in the 9-degree ply. It's a 45-degree ply or so. And these things are going to get a little bit more fun when we go things like laminate 2, which has 2 angles. And E sub phi for this, 2 angles. So for 2 different angles for E sub 2, this will be the relation as a function of phi. So if I take a plus 45 minus 45 layup, okay, and execute this is what I get. This is a plus minus 45 layup, 2 angles. So its modulus, again normalized with respect to E1. This is 1, this slice. Way lower than that. It's actually about 30%. The largest modulus is at 45 degrees, and there it only reaches 50% of the possible E1 that you can have for this laminate. So 45 and minus 45 is not necessarily very good thing. And so let's do other combinations. This is a 45 and 0 degree layup. And that's how it looks. The largest stiffness for a 45-0 layup is here at around maybe 20 degrees or so. It's pretty good in the X direction. Y direction stiffness is still lousy, a little more than 20%. It's about 30%. And lowest one is in this direction. And this was 45 and 0. Now, of course, what I will do next is put theta 1 and theta 2 here and put it into a manipulate to change theta 1 and theta 2 independently. So for a 0-0 layup, this is what I have. For a 0-90 layup, this is what I have. The largest modulus is in X and Y direction of about 60%. And lowest modulus is at 45 degrees. It's a little better than 30%, but not very high. This was a 45-0. This is what I get. Plus minus 45. This is what I get. What else can I try? 30 minus 30. This is why I have it. It has a pretty good stiffness here. Lousy stiffness there. Larger region where the stiffness quantity between 30 degrees and minus 30 degrees is fairly high, but not very good in that direction. So there may be an application where you would like this compared to this, or any other combination that you might have. Okay. Is there anything more interesting that I can show you about this? This is completely 70. This is completely 90. So plus minus 90, I think we didn't show, but it makes no difference. Plus minus 90 is like two 90s together. And plus minus 75 has a pretty large stiffness, close to 1, but still bad. Plus minus 60, plus minus 45, plus minus 30, 0.30, all kinds of interesting stiffness property distribution. Let's go to 3-plies. Same story. We don't have to spend too much time in there. We can actually go directly to polar plots and normalize one. And I'm going to be normalizing. And so this is a plus 45, 0, 60 layer. But if I want, I can put it into manipulate. Have 3 different orientation angles. This is all 0. And this is all 90. If I have 0, 90, 0, that's that. If I have 2 zeros and a 90, that's that. But let's do something interesting. 90 plus 30 minus 30 plus 30. I've got a circle. What does that mean? This is the question, gentlemen. Stiffness is the same in all directions. That is indeed correct. Do we have a name for these layups, laminates? It can be treated in its plane as isotropic. Quasi-isotropic. That is absolutely correct. A layup that has plus minus 30 and 90 is a quasi-isotropic layup that has stiffness properties in plane, same in all directions. So is 0, not plus minus 30, plus minus 60. Okay? Why do we call them quasi-isotropic, not isotropic? This is a trick question. Believe me, sometimes when, even the faculty doesn't know the answer to this question. Why don't we call them isotropic? It's isotropic. Yes, there's there's potentially a B matrix, then a D matrix. So if you're bending this laminate, it is not going to behave like an isotropic material. Bending behavior is going to be very different directions. So bending stiffness properties will depend on the direction. If I plot instead of E sub phi, if I have a D value, bending stiffness value, some bending stiffness value, I cannot easily find a bending stiffness that will be independent of the direction that we look at. Yet there are those laminates. We can actually design a laminate to be completely isotropic by making certain choices. We can get rid of the B matrix. That's easy by making symmetric, but also through the thickness location by choosing in such a way that we can turn the bending stiffness to be isotropic. But for the time being, for 3-layer layups, only these two combinations, 0 plus minus 60 and 90 plus minus 30 will give you isotropic. Plus minus 45 and 90 is not isotropic, though it's not too bad. 0 plus minus 45 is not. If I do this, I get some even strange plots in there that have skewed properties and things that will be all over the place. But this tells me everything that I need to know about the directional stiffness properties of the different layers. So based on this, let's do one more 4-angle. And if I do this, again, with 4 angles, this is all zeros, that's that. And you would get more possible quasi-isotropic than with 5 layers. That is correct. So with this, with 4, we have 0. The well-known one is plus minus 45 and a 90. So 0 plus minus 45, 90 is a quasi-isotropic layup. Now, is 0 or say 90 plus minus 30 and 90 quasi-isotropic? No. Nor is 0, 0 plus minus 60. It's not. So one last thing that I want to show is with 4 angles, this is the only quasi-isotropic layup. With 5 and 6 and 7, you will see actually there will be more opportunities. In fact, you can use every one of these angles in the layup. If you have enough many layers, you'll also get a quasi-isotropic laminate. One final thing that I want to show you is the magnitude of the stiffness for between 3-ply quasi-isotropic and 4-ply quasi-isotropic. So for 4-ply quasi-isotropic, plus minus 45, 90, I have about 50% of the E1 is achievable for me, about 50%. Let's check the 3-ply, 0 plus minus 60. That's also about 50%. Is it a little less or a little more? You have to actually look very carefully, and they are the same. Okay? So there is no difference. But of course, people will prefer using plus minus 545 4-angle quasi-isotropic more than the 3-ply, simply because differences in the D matrix and D matrix bending matrix would be larger for the plus minus 30, I believe, than this one. So it's closer to being isotropic, but not isotropic. But they're both quasi-isotropic. All right, so I created this module now that's called polar moduli, and it can give you the effective stiffness F, GF, nu F. So say for this layup and layer thickness of 1, apply material again glass. I can compute the U vector, and if you call polar moduli, you need to read this a little bit more carefully. It says it gives you E, G, nu. So if you take it has two options: effective moduli index. The default one is 1, and normalized true. Default value is true. So if you want the effective moduli in the one direction, second direction, you put 2. That will give you G. And if you put 3, it will give you nu. So when you run this, I can run it E sub V, polar moduli. This is default value of this. And this is the E, and I kept this up to 2.5 instead of normalizing with respect to 1. Because as you will see, G value for this can be actually larger than the base value, and this is a 0 plus minus 30 degree layer. 0 plus minus. If I made it quasi-isotropic, I could have done this 60 minus 60. Let's see what that does. This is quasi-isotropic, E value. G value is also here. That is quasi-isotropic, G. But if I take the G is actually larger than G12. This is normalized with respect to G12. So G value is larger than the single layers G. If I make this again 30, I want to go back to 30 again. And look at G. Actually, G is isotropic, although E is not. And nu, which is the third index, optional, is not isotropic. Well, this is the interesting thing about G. Once you put a layup with 0 plus minus 30, your G value is automatically, and it has a value. But if you put plus minus 60, that's also isotropic, but it has a larger value. So we can show all three in one plot: E, G, and V, nu. And you can see their relative values normalized with E1, G12, and nu12 values. So you can basically do a bunch of things, and if you want to put more layers and try to use manipulate and let the orientation angles be variables, you can see how different ones are all changing in one plot. Okay, so it could be a very useful design tool for somebody who just wants to design the stiffness properties. that, I conclude my tutorial. You can run these, the rest of it yourself. This is for a laminate 93 plus minus 60. I don't know why I ran that. 090, 0 plus minus 60. You can see their behavior. So this is 0 plus minus 60. EG knew everything as quasi-isotropic and their relative values. This is 090. They are all not isotropic. So this is not a quasi-isotropic layup. 090 is not. It's all like flowers. This is the laminate 60s. G is quasi-isotropic, but E and nu are not. Okay? That's it. That's the stiffness design tool for the time being. We're going to do one also with lamination parameters, but that's not going to be part of the test or part of the project. We'll cover it next Tuesday. And that'll be it for today. Unless you have questions and you want to stay for an office hour. I believe we do have an office hour this time of the calendar, of my calendar.